Hello, this is part 2 of my review of lecture 28 on similar matrices, and here we'll talk about some bad example, and also introduce this Jordan form and Jordan block. Okay, so let's start with an example. So this is an example also in the lecture. So let's say the family, let me pick another color, the first family, which only consists of 4004, and the second family, which has this matrix. So let's just put a 1 there instead of a 0. And this family right here is a really special kind of family because the only member of this family is only this matrix. Now, why is that? So even if you have like any arbitrary invertible matrix M, and this is just simply 4 times the identity, right? So even if you multiply on the left by M inverse, and then you multiply on the right by M, you will only end up with this times this, and this you will all end up with the 4 times the identity. So you will get what you start with. No matter what kind of M matrix you put here, you will always end up with this. I have tried this on my own. I put any kind of matrix there, and I will always end up the same thing because this theorem holds. So this is a really special kind of family that if you only have this kind of matrix, which is some constant times identity, then the only member of that family, the only matrix that is similar to this matrix, if that makes sense, is only this one. So that's the first example of the first family. And how about this one? How about if I make only this different on top of it? Let's begin with analyzing this matrix. Okay, we know that, let me put a more clear 4 here. We know that the eigenvalue are both 4, right? They are 4. So repeated eigenvalues, and in case of repeated eigenvalues, we must always watch out for the not full eigenvectors, or there's missing eigenvectors in that sense, which is also what we observe here. If you do it computation in your head quickly, then you will see that this is 0 1 1 0 because you times this matrix. Let's call this A, and then this A minus the lambda I, so you end up this one, and then you have this eigenvector which is only 0 times some constant. So you only have one eigenvector, therefore this is not diagonalizable. Okay, not diagonalizable matrix. And what else? You have the eigenvalues, repeated eigenvalues. Okay, not diagonalizable, and actually that's it. But the thing is, what makes it different with this one, although they are really similar, is that this one has family, or should I say has matrix that is similar to A, has another matrix that's similar to A. So it's not like the first family, the member is only this one. It has another kind of matrix that is also the member of this family. So let's just begin with, if I cook up some matrix here, let me pull 4 3 here, because what I'm trying to imitate the trace here. The trace is 8, so I have 8 there. So then the next thing to do is, all I have to do is make the determinant equal to this one. So the determinant of this is, determinant of A is, we can compute quickly, is 16. So I need to do +1 here, so I just put here, and this is clearly similar to this one. Let's name it B. and this is also not diagonalizable. And another one could be for 4, 0, 17 right here. So the thing is, it's just some kind of matrix that is like you start with A and then you 8 minus A, you know, the trace minus A, and then you build something up here. So the whole point is that of this example, remember that this case here, that is the diagonal case with some constant time identity, it only have one member. Meanwhile, this one, which looks like diagonal, right? Like this one looks diagonal, but not diagonal. It looks diagonal. It is closest. Maybe I should put that word closest to diagonal, but it's not diagonalizable, because if this one is diagonalizable, then we will end up with this one. So this matrix here, this form, is called the Jordan form. So Jordan create this kind of the beautiful form, the most basic form in the family that is diagonal, but it is not diagonalizable. He tries to work on this case and try to separate this into two families. So this is called the Jordan form. So that's for the bad case example, and now let's move on to another example. Before moving that, another point to learn here is that see that in this family, in the second family, that they have single eigenvector, right? Only this one, only single eigenvector in all of them. So we can add that in the requirement to be similar matrices which has the same number of eigenvector. Why not? Because that's also proven in the previous example, right? It has full and distinct eigenvectors as well, and this one, it only has a single eigenvector. This also belongs in the one family, so it all makes sense right now. But it turns out even having these two requirement, these two lists of requirement of being similar is not enough to define something to be similar. So that brings us to our last topic, which is the Jordan block. Let me delete some of this example. Now I will begin with the really cruel, really bad example. So let's see this matrix. We know it has 4 eigenvalues, but all of them are 0. Because it's diagonal matrix and the lambda is sitting in the diagonal. Let me delete that. Okay. And then we know that it has rank of 2 because it has 2 independent columns here. And we know that the dimension... let's not talk about the dimension first. Let's just talk about the eigenvector. And since you know that if the eigenvalues are 0, then just to quickly remember then we will have lambda equals 0. Then it will be ax equals 0. So the eigenvectors live in the null space. And in fact, the eigenvector itself is the vector in the null space. So that's why I am bringing up the discussion about the dimension of null space of A, which is 2. So we have here 2 eigenvector. Okay, we have 2 eigenvector for this matrix. Let's not name it A. And the second example here, let's put 1 here instead of on the third column. Okay, And we still here have the same case for the lambda, 1, 2, 3, 4, 0. And the same thing also, the eigenvectors live in the null space, right? And the same dimension for the ranking 2, and then the dimension of the null space A is also 2. And we also have 2 eigenvector here. Okay, see now, it has the same eigenvector. But is A and B similar? That's the question, because we have all these attributes of declaring two matrices to be similar, right? That the eigenvalues are equal, they are all 0, and the eigenvector are also have 2 of them, the same number. But it turns out they are not. And why is that? Is that this time I will introduce you to the Jordan block. So Jordan block goes like this. So it has all the eigenvalues along the diagonal, but it has the one on top of those eigenvalue. Let me give a different color. So this is put 1, put 1, put 1, and the rest of them are 0. So where is the Jordan block in this case? Let's see. In this case, in this B, I have this one, my first Jordan block, and this is my second Jordan block. How about this one? In this case, I have, so these are my eigenvalues, 0, 0, and on top of that I have 1, 0, on top of that I have 1, so this is my first Jordan block, and this is my second. And another thing about Jordan block is that one block equal to one eigenvector. So that's why we have 2 blocks on each matrix, so we have 2 eigenvector. But the blocks are different. See? This one looks like this, and this one looks like this. Therefore, they are not similar. And turn out that's another attribute of being similar, that they have the same shape of Jordan block. Actually, unfortunately, it was not discussed further in the book, so this only discussed briefly at the end of the lecture, so that's all the information that I can get out from the lecture. Okay, and the neatest, the most neat Jordan block is when the Jordan block equals to our lambda, right? So for example, if you have undistinct eigenvalues, so you have 2, 3, 1. So how many Jordan block you have in this case? You have 3 of them. You have just those eigenvalues sitting only in 1 by 1 block in each column, in each row, right? This was all 0, 0, 0. If you remember also from previous example, I have this example for 1, and this by itself is in the Jordan form, and itself is a Jordan block. You see, the lambda sits in the diagonal, and you have 1 over there, and this is the simplest Jordan form and the simplest Jordan block. But the most beautiful case is when all the eigenvalues are defined, and you have like some kind of a matrix with the Jordan block 1, Jordan block 2, Jordan block 3, which what we have here in case of the lambda in the diagonal, and the eigenvalues are in the diagonal. So that's all for a summary of lecture 28. I see you in the next summary. Thank you.